Hi, I'm Matheus, and today I'm going to present about SweynTooth, unleashing Mayhem over Bluetooth Low Energy. And I'm going to talk most about how we were able to discover many vulnerabilities, so what was the technique that we employed to automatically discover these issues in many IoT devices, particularly for smartwatches, smart things that are using the tiny Bluetooth Low Energy chipsets from popular vendors. So this work was mostly done at the Singapore University of Technology and Design, although it was a partnership with Keysight and also A-Star. And Chundong also helped us. He started first at SUTD, but then moved to ShanghaiTech University to finish some of the work. So what is SweynTooth? So SweynTooth was a term that we initially used to describe a set of 12 vulnerabilities in Bluetooth Low Energy stacks of different devices. However, by now this number is unfortunately higher. And as we know, Bluetooth was named after King Harold's Bluetooth, so we found interesting what if we name a vulnerability based on Harold's own son, who is Swan Forkybeard. And we're not. We found problems in major vendors who sell the Bluetooth chipsets. In the range of the products that they are used, it goes from smartwatches to smart locks and also trackers. So if you have a smart device which uses Bluetooth Low Energy, the chance is high to be using a chipset from one of these vendors, even though most of them have patched against these vulnerabilities. We also found some standalone stacks, protocol stacks to be affected. Particularly for our embedded cordial, we found a track on GitHub that pointed that they also patched against one of the vulnerabilities. Before we start the work, we had to first get localized on how the Bluetooth specification categorizes its technologies, and we can understand basically 3 different flavors of Bluetooth present on these modern devices. So the first one we introduced was Bluetooth Classic, or basic rate, extended data rate. The latest one was low energy, but many devices supports both technologies, so they operate in this dual mode. And they have many similarities in the protocol, but generally low energy is a slightly lightweight version of L2CAP protocol there. And interestingly, if we look back at the history of vulnerabilities affecting Bluetooth, we starting from 2017, which had a big one, Blueborn. It mostly affected a certain implementation of popular stacks and some tiny bits of specs there. But each preceding year we had a different vulnerability, if not on the implementation side, on the specification side. So for example, we had this invalid curve attack, 2019 knob, and then bias this year, so in the specification. And this exemplifies that Bluetooth specification itself is complex, so it's common that there is also vulnerabilities that were not found before. It is still a problem that Bluetooth by itself, as being a wireless technology, is difficult to test, so it takes time for these vulnerabilities to be found. But nevertheless, we realized that there is not much work done in Bluetooth Low Energy, particularly implementation faults on the low energy side, so that's why we focused only on Bluetooth Low Energy in this work. And the context that 2 devices in a Bluetooth Low Energy network operates, they have different roles. And for example, your smartwatch, which is called the Peripheral, is always announcing itself to then your smartphone, which is the central. So there's also this default way that our Peripheral always advertises central connects to, even though there could be different combinations. But nevertheless, the way that, for example, developers implement their stack is to use the support of the standard test equipment for Bluetooth, which is later on used for certification. And these equipments are really expensive, so they can be like around $10,000. Because they are not only made for capturing packets over the air or testing the performance of your equipment, but they also test the quality and other complicated things on the physical layer part, and also because of the certification. But so we are not interested in testing all the parts of the technology itself, but only on the protocol itself. So then one question that we come up is, can we avoid this setup, right? And the Bluetooth protocol stack is not simple, so the complexity of its message sequences makes it a bit harder to test the security overall. So if we want to summarize the main procedures, we can described as the first one will be the connection, when the peripheral and central switches from the advertisement channel to the data channel when they exchange actual data. And then the pairing procedure, which then performs the establishment of a common key between central and peripheral. And lastly, the link layer encryption, which only happens on the controller side. Another important point of why it's important to have access to the link layer. We then try to think in a way to test all those procedures that I was shown before of Bluetooth Low Energy, and also how to have in mind how the fields exchange between two devices. And one thing that happens in software is fuzzing, and fuzz is really good to test different programs with different inputs, because it's really fast, and you can also combine with evolutionary mechanisms to try different inputs and then try to reach different parts of a program and eventually find vulnerabilities. The challenge is that there is no much work on the wireless part, doing the same for wireless part. So the first challenge that we arrived when thinking how to adapt the fuzzing design for low energy, and first of thing, how to access and also have full control over the link layer, right? And the other is that there is also this sense of the feedback, and how you can get a feedback from the device that you are testing to try to improve the fuzzing, because over the air things are slower, so it's relevant to try to optimize and send the most relevant inputs as we can. And also Bluetooth is a heavily stateful protocol, so for every message exchange there is certain sequences of messages, also some optional sequences that needs to be taken account. So we need to think in a way to send not only mutated inputs to the peripheral, in this case that you are testing, but also messages out of order. Then this is particularly important to discover new vulnerabilities that the reason why they appeared was out of order messages, and also how to detect crashes or anomalies. That will depend a lot on the setup of the device that you are testing. We then begin by taking on the first challenge on how we can send link layer packets from the center to the peripheral and back and forth. And it turns out that we can use the tiny microcontrollers, which has internal radio support for Bluetooth Low Energy. And one of these devices is this NRF52, a device that you can program yourself and implement a controller from scratch. And because it has support for USB, that will be the perfect setup to integrate the fuzzer. In elaborating the design itself, we elaborated this firmware and call it a non-compliant firmware, because we are implementing it to the whole goal of this design is to forward packets, link layer packets to and from the center and the peripheral. And because HCI is not sent over the air, it is possible to move the link layer from the controller to the host. So we are eliminating the total need of the HCI by creating the link layer procedures totally on the host, more precisely on the model of the low energy protocol, and only handling on the firmware the essential time-sensitive tasks such as channel hopping, and also detecting the correct channel to switch to and from, while they communicate with the peripheral. This was actually really useful for the fuzzer to send arbitrary packets even during the connection procedure, which we found really basic vulnerabilities there. We then introduce the Fuzzer architecture, which makes heavy use of this access to the link layer. And we introduce the first component that is common for Fuzzer is the packet manipulation. But the caveat is that we are aiming here for mutating specific fields depending on some sets of values, which I'm going to show later. And also introduce this packet redundancy, which is to send packets in the wrong sequence. This is particularly important to try to find new paths with the vendors of the stacks they didn't think of. And lastly, the packet validation, which is essential for discovering anomalies which may arise due to either the packet manipulation, redundancy, or combination thereof. Also the state machine, which we choose to create our own state machine as to increase the flexibility, later on replicating the proof of concept and also adding the conditions so we can ensure a better validation. And of course, to optimize the packet manipulation block, we employ also a fuzzing and optimization block there, which uses the cost function which comes from the model itself. We then showcase more in depth how the mutation works, but the intuition is simple in a way that we assign probabilities to each layer and fields within a Bluetooth packet. So by layers, I mean the different protocols contained within a packet. And whenever the fuzzer tries to go inside of this packet to iterate over, it looks first on the layer probabilities and then enters the fields and then tries to mutate the fields based on the probability. Now the important thing to mention is that we are assigning the same probabilities for all the fields of the same layers. This is to simplify the optimization part. And we then flatten all these probabilities and then assign to a state. So here we showcase the packet redundancy component, and the intuition behind this is that whenever there is a packet going through this component, it's going to be stored on this packet history. And for example, here we have state 1, which then goes to packet 1, and we proceed, send this packet over there, and then we go through state 2, which then this component receives packet 2, and now we move to state 3 and then receive a new packet 3. But whenever we make this decision of saving the packet and then before transmission, there is a certain chance that the previous packet saved on the history is going to be transmitted just after the current packet. So for example, here packet 1 is randomly chosen. Keep in mind that the weights that we attribute for this random choice is the choice of not picking a packet from the history is higher than whenever picking, because otherwise forever packets sent in the state machine, there are going to be a redundant packet and the state machine will not proceed fluidly as the way that we want. So when the packet is the previous packet is picked, like this one, packet 1, it's going to be sent just after the current packet, in this case packet 3. And this after it is sent, it's still on the same state. It's not saved on the packet history. And then, assuming that the peripheral does not misbehave, we proceed normally to state 4, which then receives a different packet. As for the validation component, the way that we perform this step is to assign different rules for different states, and depending on whether the response of the peripheral should be normal or not, we detect if it's valid or not. So for example, we have here the states, and each one of these 3 messages represent different scenarios. So for the first one, the message would be classified as incorrect if the layers or the types of the protocols on its packet does not correspond to the expected layers of a particular state. So for this case, I'm pairing request and I'm waiting for a pair response, which is only true on the second message here. Now the rejected layers we use whether we are expecting the peripheral to receive a failure message. So this happens when we mutate, for example. So message C, supposing that we mutate the pairing request, we are expecting a message such as SMT failure, which is then valid in this case. If C would be not correspond to this value and would correspond to a different normal response, then this would be an anomaly. And just to exemplify, in a real capture, a LLAD deadlock would correspond to the first response, whereas we send a request and the response is completely wrong. Now, following up from a more complex example of the validation, which will help to detect the vulnerabilities which may arise only if after sending mutation followed by a redundancy, so out of order context here. And in this case, we start on this list of services, and we send a request and receive a response which is on the expected layer, so the response is valid. Now, showing here also the captures, we proceeded to the next state, which is the pairing request. But we send a mutated packet. It turns out that one field key size is mutated. But then the peripheral, instead of responding with a failure message, it actually responds a normal message. And so in this case, the response is marked as invalid and then flagged as an anomaly. But one more problem arises because on the same state, the packet redundant block triggers by sending a previous packet from the history and send an encryption request. Because we are not finishing the pairing request and this packet is not supposed to be sent in this order, this also yields another anomaly as the peripheral cannot respond to this request here. And then this is what happens to the key size overflow vulnerability of one of the peripherals there crashes after this sort of sequence. Well, what we have the mutation followed by out of order packet. So lastly, we have the optimization component, and the idea of this is to leverage the state model of the Bluetooth Low Energy, which then starts each iteration of the scanning phase where the sensor waits for the peripheral. And as I stated on the explanation of the mutation component, for each state has its own sets of probabilities here assigned to each layer in fields. So we assign to the optimizer all those probabilities as a flattened array. So every iteration it tries to improve by using a custom function such as the total number of anomalies and crashes. So we are not using other custom functions such as timing, because therefore in the case for Bluetooth Low Energy that can vary a lot. So using as anomaly, our goal is to focus the fuzzing and the parts that are mostly causing issues, and then we can arrive at a better conclusion where there is more security problems there. We go then to the validation setup, and we show here in this table all the boards and devices that we use to test the fuzzer, and each one you can see that they have different sample codes. And the way that it works internally, each one of these Bluetooth chipsets, they have here the part for the user code, the SDK API, which is public, and then the BLE stack, which is just a static library or binary blob that you can just link to your application. So you need to use a programmer to flash all these sample codes, the development board, so you can start the testing. So this is the setup. You're gonna notice that there is one board here that we didn't use, as we reported this after we discovered later. And basically the workflow that we use for the evaluation setup is we start by getting the development board. Then we just need to flash the sample code. Sometimes we need to modify a bit the sample code to enable the features we're going to test. And we configure the Bluetooth address on the fuzzer. After running it, we get the reports, and we just need to verify if everything is okay. And also because even though the fuzzer detects anomalies, it's not automatically security vulnerability or security bypass. So you need to identify and distinguish what can happen there. And of course, create the POC to the proof of concept to replicate the vulnerability so you can report it. And then the cycle starts over, and by doing that you actually get a lot of problems, and all of these boards here we found at least one issue. We then go forward with the evaluation, and unfortunately the current state of Bluetooth is there's not many public available tools for fuzzing, and the ones that exist, they are mostly around the Bluetooth Classic. Another thing is that the protocol that they support, L2CAP, does not exactly fit the model for Bluetooth Low Energy. So much of the packets sent by those fuzzers will be discarded by a Bluetooth Low Energy device. Nevertheless, they use some more primitive strategies such as random or using a database, for example. Another thing is that they only detect crashes, and as of compared to other strategy, they cannot find logical problems or anomalies. And of course, they cannot reach link layer as they run only on the host and depend on the HCI to operate correctly. We then create a variation of our fuzzer to better depict the different behavior of each individual component, such as the mutation and redundancy. And we show them in a graphic. On the vertical axis show the anomaly count, in the horizontal the number of iterations. And this shows that if you try to enable the fuzzer only with one component or another, it won't find all the vulnerabilities, as they may depend on certain behaviors to be triggered. So it's always the case that for when evolution is enabled, it can detect all the combined anomalies or vulnerabilities of the other cases. And it's the number of anomalies can also increase a lot if the devices affected has anomalies in a lot of different states. So two examples of that is the NXP device, which has the LED deadlock. It responds badly in different states, and the T-Link, which also has many anomalies and vulnerabilities spread across many states. Then it triggers, it yields on the fuzzer a higher number of anomaly count there. And overall, the evaluation it was relatively fast, although for the Cypress and XP was particularly fast because the first vulnerabilities found were where the crashes were triggered. It was on basic fields such as the link layer length, and for the ST microelectronic devices, it was more of a a timing issue on the link layer, which was possible to trigger when sending host layer protocol. So this shows up that just by starting the fuzzer with our design and by exploring the link layer, it was already possible to trigger some basic vulnerabilities, even though these companies may use really expensive equipment to test. Now, as to find our results, we have categorized our findings into crash, deadlock, security bypass, and anomalies. The anomalies represent the responses from peripherals which we found to be non-compliant to a specific section of the standard. But the interesting thing is that two of these security bypasses are linked to a misbehavior which is not well explained on the standard and lets out of order packets being present during the pairing process. So when this happens, the security of these two devices fails at some point, and for the date skip, it's a bit less serious because it relies on a previous stage in the pairing process, but it's still possible to bypass the security property defined on the standard here. Another thing is that there's a widely spread non-compliance regarding to the connection procedure, which a certain field can be outside of what is specified on the standard. And then there's this question why this certification didn't catch it if it's a basic field. So that was an observation that we did. Now this was the second batch that we released, so a bit more devices were affected, but the vulnerabilities were less serious because it was mostly a crash and a deadlock that we found on some other vendors. But particularly the silicon vendor reported that some of its clients were affected by the disclosure. As for the impact, we performed this test with real products such as Fitbit, EV Energy, also Smart Lock, so each one of some few categories of smart home, and we have released some two videos showcasing these attacks on the devices. And recently, for one of these devices, this could be tagged here. It's vulnerable to the public key crash, which uses the One Texas Instruments device. And it's just the vulnerability is a crash by itself, but because the product vendors forgot to implement the watchdog timer, which is a feature to automatically reset the equipment, the tracker cannot be resetted until we manually open up it with a screwdriver. So that was actually a fun observation about this. So as for the disclosure process, we released the first batch on 9th February this year. And we also released the exploit repository on GitHub, but before that we gave 90 days starting from the last vendor we contacted. However, for the second batch we held up a bit more as there were some concerns from some agencies regarding what other vendors could be affected. And but as of the day of recording of this video, only one silicon vendor did not patch and install the SweynTooth vulnerabilities. As for the final remarks of our work, it is interesting to see that the certification does not prevent a bad implementation, neither a stack free of non-compliances to be present in a commercial product, even if the non-compliance is basic. And there could be better explained some parts of the specification, particularly regarding what happens when there is one procedure starts on top of another, such as encryption and then simultaneously with SMP pairing. This was the root cause of two of the security issues that we found. And work also shows that over there fuzzing is still relevant. So given that you give it access to the lowest level of a wireless protocol, it's possible to find many issues there. This sparks another questions regarding what happens to other protocols regarding their security. Are they secure, or they are as vulnerable as the discoveries that we found, such as BLE mesh or also Wi-Fi mesh, maybe 5G or even NB-IoT. So in general, we believe that more fuzzing tools are needed to cover these other types of technologies. And overall, I believe that this was a lesson learned for the industry. So we believe that the product vendors may rethink better on what are the chips that they are using in their products and opt for the vendors that are more transparent in regards to their process and notify them early when there is a certain disclosure or patching process. And of course, the Fuzzer is available open source, open request to our SweynTooth email. But independently of that, the exploit tool and the driver firmware is available on the GitHub repository, where everyone can try out test the scripts, and also have access to the link layer to do their own experiments. So thank you all for your time. Feel free to reach us by our email.